Hey guys, today's video is going to serve as a quick review of organic chemistry and really just some things to kind of consider as we near our upcoming AP Chemistry exam. We see organic chemistry a lot in the context of other material, right? Organic chemistry is officially not part of the curriculum for AP Chemistry, but again, I think to have a little bit of background as we perhaps encounter it in future problems and past problems, probably not a bad thing. Just make sure that all of our bases are covered, okay? So as far as organic chemistry goes, just recall that this is the branch of chemistry that deals with carbon-containing compounds. We're going to jump right in and talk about alkanes straight away. When we talk about alkanes, just recall that alkanes only have carbon-carbon single covalent bonds. Here are the common prefixes we use. To name an alkane, we simply toss on the suffix ane. So for instance, should we encounter a molecule like this that has two carbons, we would use the prefix eth and the suffix ane, and we would call this ethane. For a bigger molecule, let's say we encounter something like hexane. I've chosen to draw this one with kind of the correct geometric arrangement of atoms as far as expressing like the tetrahedral arrangement around the carbon atoms there. But this is C6H14. The reason I wanted to use ethane and hexane, again, hex coming from the fact that this is 6 carbons within the backbone here of the carbon chain, is I just want to kind of do a quick review concerning what we see here as far as properties. What we find is that for hexane, we have a substantially higher melting point and boiling point. And again, the reason behind that is because hexane, well, first I guess we should identify that both of these are nonpolar molecules, right? And if both of them are nonpolar, the only type of intermolecular force that would need to be overcome as we transition, say, from solid to liquid in the case of melting, or perhaps liquid to gas, in the case of our boiling point, would be intermolecular forces, right? We need to overcome intermolecular forces. In this case, we're only talking about dispersion. So, in the case of hexane, we would say that hexane has a larger electron cloud, therefore it is more polarizable. This polarization, increased polarization, I should say, leads to a stronger dispersion force. It therefore takes more energy to overcome this stronger dispersion force, and subsequently we see higher melting and boiling points, okay? Moving right along, I want to get into what we call functional groups. When we talk about functional groups, these are groups of atoms that are largely responsible for properties of the parent molecule. So in this case, when we move on and talk about alkenes, we're talking about molecules that have at least one carbon-carbon double bond. And we're not going to go over the reactivity, but this carbon-carbon double bond here confers special reactivity to these molecules. You might recall things like a cis or a trans designation, which really just expresses the orientation of the groups on the carbons that actually make up the double bond. We won't go into that quite yet, or in this video, I should say. As part of our quick review. Moving on to alkynes, again, kind of stemming from our alkenes, we're talking about molecules that contain at least one carbon-carbon triple bond. And so let's say we're given the formula C2H2. If I wanted to draw this thing, I have a carbon-carbon triple bond, and I have some hydrogens kind of out here in the wings. Just a quick check, carbon is 4 valence electrons, so there's 8 electrons coming from the carbons. Hydrogen has 1, so there's 2 total electrons coming there. So we have 10 electrons we get to play with kind of in our Lewis structure. 2, 4, 6, 8, 10. That checks out. And we've satisfied the octet rule for our carbon and the duet rule for our hydrogen. Here we only have 1, 2 kind of electron groups around that carbon, making that sp hybridized. If we wanted to talk about this triple bond here, we would say that there's 1 sigma bond and there are 2 pi bonds. Moving on to, I think kind of more interesting functional groups, we get into our alcohols. And the next actual couple will contain oxygens. So alcohols contain the hydroxyl functional group. Oftentimes we'll see it represented like this. Just recall that the oxygen is going to have 2 lone pairs, and subsequently we'd have a bent shape on that oxygen. If I wanted to draw this out really quick, given kind of our condensed structure here, it's going to take just a quick second, I suppose. Drawing all my hydrogens for good measure, which you always should draw in all atoms and Lewis structures and indicate all lone pairs when necessary. Here's our structure for 1-butanol. And again, we won't go into naming conventions quite yet, but the alcohol, that hydroxyl group is at the 1 position because we would number 1 over to 4, and the hydroxyl group gets the OL designation. Of note with alcohols is that they can form hydrogen bonds with themselves, right? So 1-butanol can form hydrogen bonds with another 1-butanol molecule, those intermolecular forces, but they can also form hydrogen bonds with water, and therefore that favorable intermolecular attraction would lend them to being miscible, right? They would mix in order to form kind of a homogeneous mixture. As the chain length of this carbon chain increases, say we go from 4 to 6 to 8 to 10, that molecule becomes increasingly non-polar. And though it would have a very kind of polar area of the molecule, its miscibility or its ability to dissolve in water would be diminished. Okay. We'll move on to the 5th functional group that we're going to talk about. We're only going to work through 7 today. Is that of our carboxylic acids. Carboxylic acids aptly contain the carboxyl group, or we might call it a moiety. It's kind of the fancy term for that. Often we see it represented as COOH, or like coo. I'm not really sure why I did that. Here's what that carboxylic acid group or carboxyl group is going to look like. We have a carbon double bonded to an oxygen that has 2 lone pairs. And then we have kind of the OH group here. Again, I've kind of actually written this out with the 2 separate lone pairs. If I wanted to draw this Lewis structure as far as representing correct geometry, making sure I knock out all lone pairs. Maybe I have something like this. This is actually going to be ethanoic acid right now that I'm drawing. Again, there's 2 carbons. The oic acid is the suffix we would use when naming carboxylic acids. We might even call this the common name acetic acid. Okay. Now, as the term acid might imply, it has an ability to lose or donate a proton or a hydrogen, which is why they act as acids, right? But they are weak acids. They're not the one of the 6 strong acids I've asked you to memorize throughout the course of this term. They can form hydrogen bonds, again, not only with themselves, but with water molecule. So assuming that the chain length is rather small, we would expect these molecules to be miscible or mix with water. Now, if it is an acid, and let's say we remove, that hydrogen there, it gets plucked off by a base or, simply a water molecule, acts to deprotonate it. What we get is the following. We get a 3rd lone pair of electrons on the oxygen atom. This gives rise to a -1 formal charge on that oxygen. And this is the polyatomic ion acetate. Okay, so again, that's carboxylic acids. We'll move on and we'll talk about ethers. Ethers are pretty distinct. They have this like RORO prime group here. And basically what we have is a carbon chain where there's an oxygen actually embedded within the carbon backbone. So given this condensed formula, if I wanted to kind of draw this out, I draw my oxygen here in the middle. I got my carbons in the wings. Again, I'll draw in all my hydrogens just for good measure. Now this structure, as far as a Lewis structure, would totally be accepted on the AP exam. That being said, I'm not really expressing the correct arrangement of atoms around, say, the carbon or the oxygen, right? Where we'd see a tetrahedral shape around these carbons, and we'd see that bent shape around the oxygen there. That actually makes this molecule, which, by the way, is diethyl ether, it would actually make this molecule semi-polar. It's mostly non-polar, but there's a degree of polarity to it. It has the capacity to form hydrogen bonds with water, but it has limited solubility, I believe, if I remember correctly. Even though it's like kind of ish polar, there's a very, very slight dipole moment. We largely classify it as a non-polar solvent, despite the fact that we're going to have a bent arrangement here and kind of a polar bonds and maybe a slight dipole moment. Just of note, if you take a look at these two formulas and you actually counted the numbers of carbons and hydrogens, what you'd find is they had the exact same number. And in fact, this is the formula we saw in example 4 under our alcohols. This was our 1-butanol. And so the idea between 1-butanol and diethyl ether is that while they have the exact same formula, clearly, structurally, they are not the same. And so we call these things isomers of each other. And kind of generally speaking, they are structural isomers. We might get a little bit more specific and call them functional isomers. One of the big differences is that 1-butanol has this capacity to form hydrogen bonds with itself, right? This molecule can form hydrogen bonds with itself. This oxygen, because it lacks a hydrogen, cannot form hydrogen bonds with itself. So for diethyl ether, we're talking about dispersion forces and maybe slight, dipole intermolecular attractive forces there. But we would expect 1-butanol to have a much higher, or certainly at least higher, boiling point, I would guess, than that diethyl ether. Okay, but again, we'd want to have data in hand. It's possible. Nope, I suspect that would be the case. That 1-butanol would likely have a higher boiling point, okay, given the hydrogen bonding capabilities as opposed to the non-hydrogen bonding and therefore weaker intermolecular attractive forces there. The last one we're going to talk about is our functional group amines. Amines are organic bases, okay? Having the general formula R3N, where really R can represent hydrogens, they can represent carbon tails, whatever the case is, but we need to have that nitrogen in there. Now, given this term bases here, the reason we're talking about amines, because there are tons of different functional groups we could have focused on, is their ability to act as bases. So let's say we subject ethylamine, which is this molecule here, kind of written out. This lone pair right here has the ability to attract a hydrogen, right? It has the ability to accept a hydrogen. So if ethylamine is exposed to, say, hydrochloric acid, it can become protonated. It can gain a proton, and that's what we see here, right, on the product side of things. So I've actually taken out the ethylammonium bit, and I've drawn it out, where down that nitrogen we find has formalized a covalent bond with the hydrogen. Subsequently, it's picked up a +1 formal charge, okay? So this acts as the base. This over here is our conjugate acid, okay? So amines can act as a base. Again, if you take a look at the structure, obviously it's capable of forming hydrogen bonds both with itself and with water molecules. Thanks for watching, guys.